So, Muneendra sir, shall we start?
Okay, sir.
Okay. So, very good morning, one and all present here. I, Dr. Lal Pratap Verma, welcome you all in day 3, session 1 FDP of FDP, Deep Learning and Computer Vision. Today's first session speaker is Dr. Muneendra Ojha from IIIT Allahabad. Before inviting Dr. Ojha, I would like to read the brief profile of him. So, Dr. Muneendra Ojha is working as an assistant professor in Indian Institute of Information Technology, Allahabad. He has done BSc and MSc degree from Institute of Science, Banaras Hindu University, Uttar Pradesh, and done MS from University of Missouri, Columbia. He has done PhD from Indian Institute of Information Technology, Allahabad in 2007. He has more than 10 years of teaching, research, and industry experience. His research interest is deep learning, natural language processing, video analytics, semantic wave, multi-objective optimization, genetic algorithm, and multi-agent system. So this is about our today's speaker. So Muneendra sir, over to you.
Thank you, Dr. Verma. Thank you for inviting me and thank you for sharing my profile. And today's lecture, as you all know, I'm going to talk about convolutional neural network. At this moment, I welcome all the participants and I wish you all a very happy and healthy new year. With this, let me share my screen. I hope my screen is visible to you.
Yes, sir. Yes.
All right. Okay. So in today's lecture, I'll be talking about convolutional neural network and how we can utilize CNN for classification tasks. So in this lecture, I'll be talking about the fundamental details, theoretical understanding of the CNN, and then I will give you a brief idea of how to program CNN so that we can utilize it for the classification task of images. For that, I will take one toy example, which is very famous example, and you would find code and data of it over Kaggle and many other websites which host the data sets for computations and machine learning computations. So with this, let me start. Okay. So why was there a need of convolutional neural network? See, there is a need of understanding images, and we all know that we are trying to make our computers more and more intelligent. But what is intelligence? We say that the very thumb rule of intelligence is that if a machine is able to do what humans are doing, then that is intelligence. Okay. So humans are supposed to be intelligent species. So if a machine can do what a human can do, then the machine is intelligent. However, the intelligence idea or the artificial intelligence that we were trying to imbibe in the machine in 1930s and 40s and 15, that did not suit well because that was a very long step imagined ahead of time. So then people realized their mistake and then started introducing incremental intelligence. Okay, intelligence in short span, intelligence in very small amount. And in that part, the one of the challenges which people faced was identifying images, recognizing images, detecting images, understanding images. Okay, because images are a big part of our whole understanding, vision, day-to-day life. What we see are images, what we run through our images, what goes in front of our eyes are images in a fast way or sequential manner. So there are 5 sensory organs, okay, and in humans. So to represent eyes and then what eyes see and how our brain perceives it, we need to have a proper understanding of what people are looking at, means images. So if we pass this intelligence, or if we pass, I would request everyone to please mute themselves. Thank you. So if we pass our intelligence to a machine, the machine should be able to see an image, detect an image, understand that image, and understand in a way that it should be able to identify what is there in the image. So in that regard, the first step was to identify a human face. Okay, that was one of the problems that was posed in front of scientists, that how can we create a machine which can see, which can look at an image, and then from that image it can identify a person, a human, and then very precisely find out the image of that represents the face of a person. Okay, so like in this image, as you can see, we have the former president of United States of America, Mr. Barack Obama here, and very well we can identify his facial features, his face, and we can without even thinking, we can definitely identify who this person is, where his face is in the image. Okay, so this problem is not a very significant problem for us. Of course, there might be many people who do not recognize Barack Obama, but definitely there, I don't think there would be anyone on this earth, any person on this earth who has a sound mental ability and will not be able to identify where is the face of this person. As this bounding box, there is a green bounding box surrounding the face of the person, whoever the person is in the image, and this bounding box represents the face of the person. This bounding box is not telling us who the person is, it is not recognizing the person, but it is detecting the location of the face, it is detecting the face. So any person with a certain age, I'm not talking about um, uh, children, newborn babies, but I'm talking about any grown person. If you give the person this image, the person would be able to identify and detect where the face is. If there is a possibility the person might not be able to identify who the person is, but definitely the face location will be identified. So if we pose this question to the machine, how will the machine react, how will the machine be able to identify and detect the location of this face of a normal person? This was a question, and it was dealt in traditional machine learning approaches by different features identification. So these features were how the face would be, what should be there in the face. Like you see over here, the face has a pair of eyebrows which are horizontal kind of, then a pair of eyes just beneath the eyebrows, then there is a nose bridge between the uh, eyes section and the lips or mouth section. Okay, so this is a kind of H which was being created. So H, a horizontal H, a H which is lied down. So I'm not saying I because the upper and lower portions are longer than the middle section. So I'm saying that H is inverted. Anyways, so this is the way people try to identify, and in this paper, which was a seminal paper by Viola Jones, the authors tried to identify the features, unique features of a face. But whatever you try to describe about a face, that face is a there might be possibility that you are not looking straight at the face. Okay, like in this paper, they tried to identify the faces had certain patterns of light and dark patches that can be exploited. For example, there is a difference in light intensity between the eye region and the upper cheek. Okay, so you see there is this eye region which is hidden with this filter, and just beneath it there are cheeks which are a shade lighter. Okay, then there is also a difference in light intensity between the nose bridge and the two eyes on either side. So there is a nose bridge, as you can see. I would request you to just give me a second. Okay, one second, one second. हाँ आ जाइए अच्छा, मैं जरा एक क्लास में हूँ तो मुझे फोन मत करिएगा, आप डायरेक्ट घर पे चले जाइएगा, ठीक है? आई एम सॉरी. All right. So there were several shortcomings. So these were not very effective ways to identify features by themselves. Each of these feature is not very effective. As you can see, if the person is not looking straight, then you would not be able to identify the difference between the light intensity between eyes and the face cheeks color. So, but when these were used with machine learning methods, the latest machine learning techniques, this method actually gave very good result from the corresponding state of art. So, contemporary at that time, whatever was the state of the art in artificial intelligence, with respect to that, this paper gave very good result, and it was able to identify on a data set of 130 images and 507 faces. The algorithm achieved an accuracy of 91.4%. So it was just trying to detect a face, okay, and it detected 50 false positives as well. Performance was unparalleled at the time, but there are fundamental limitations of the algorithm. If a face is partially covered, it's in shade, the light intensity comparisons no longer work. If the algorithm is looking at a face on a crumpled flyer, then also it will not be able to identify, or probably the face of a cartoon character. There is no light intensity different. All the features are just made in one intensity, one color shade. So how would the machine be able to identify? These were the challenges, which are the shortcomings of this traditional machine learning algorithm. So coming from the traditional, we went into deep learning towards 2012. This paper by Alex Krzyzewski and Geoffrey Hinton, the AlexNet came into picture, and of course, when this paper came, a lot of things were already in motion. A lot of people were working on deep learning, and the research before deep learning, the artificial neural network research was already going on. So this research never ended. Actually, AI goes through several stages of AI winter. So it has seen AI winter towards 1950s, 60s. Then in 80s, it was very good and a lot of things were happening. Then again towards 90s, it saw 90s and early 20s, it saw an AI winter. Then with the advent of parallel processing and the parallel processor, the GPU, the graphics processing unit, the parallel processing came to fore, and this neural network research started being implemented on GPUs. So what happened that the neural network, as you can see over here, there are two different neural networks created on the screen, shown on the slide. And every node, as you can understand, because it's the third day, I hope you have a fair idea of what a neural network. So these are the nodes, and each node computes some functions. It's a neural network. What is neural network? Neural network is nothing but a composite function. So every node is representing a function. It takes a weighted sum and then passes it on to an activation function. Activation function produces an output. This is the role's responsibility of every node. So this is the responsibility, and suppose every node is working independently of each other, then why can't we have these computations on parallel computing units? So that was the idea, and with the advent of GPUs, the whole neural network computation was projected onto given to the GPUs, and it created wonders. It actually started giving results in very small amount of time. So before this, we used to run these on sequential CPUs and through MATLABs. So MATLAB itself is a very bulky software. I remember when I made my master's thesis, master's project for handwritten digit recognition. That was my master's thesis through neural network. We had to run it on MATLAB. There were no programming languages which could actually efficiently program these. So we had to do it in MATLAB. It was very tough in those times. We had only Java and C++. So we did it in MATLAB, and then through MATLAB, the MATLAB itself was very bulky, and when we gave it a huge amount of data set, the whole computation became very bulky. and we were working it on CPUs. So through 2007 and 6, when the GPUs came, the neural network research became very fast, and a lot of experiments started happening on neural network. And with that, the research was already going on. You understand, the Geoffrey Hinton group, and then Alex Krzyzewski people, the young PhD students, and the previous Jan LeCun, all these scientists were working in artificial neural network, and they were giving some algorithms. However, these algorithms were not being tested and implemented on fast machines, so they could give better results and in time. So what happened, you would create a neural network, and after 1 month, if you are going to observe the result of it, it might be poor result, it might be very good result, but after 1 month, you lose the idea, you lose the charm, you lose the motivation, and you lose the way your thinking was happening, that if this would happen, I would do that, if that would happen, I would do this. So when people started getting,
Yes, sir.
yes sir,
I think the slides are not moving.
no, it is static. I have not moved it.
Okay, okay. Thank you.
So when people started getting results, they were able to judge what is the drawback, what is the efficiency, what are the pros, what are the cons of the algorithm that they have created. And this way they were able to make better and better algorithm. They were able to improve their algorithm once they started getting results. So from 2007, with the advent of GPU by NVIDIA, till 2012, when the Alex Krzyzewski paper of AlexNet came up, the deep learning had taken very long steps and has run through a large stages of advancements. So now we are talking about deep learning and how do we do classification through deep learning neural network. Let's move and see what this actually is. So as you can see over here, there is a deep network which is in the 1980s era. The neural network were like this. They were very shallow, one hidden layer or two hidden layer maximum. If you don't dare even to go beyond two hidden layer, because we were thinking that okay, there is no possibility, because we will not be able to get the result. Now we have got multiple hidden layers, and the network is getting deeper and deeper, because we start from left hand side as the input layer, and we run through several stages of hidden layer. That is why we that is when we reach the output layer. So we say the network has become very deeper. That is why the term deep learning or deep neural network has been coined. And every layer performs some functionality. Like over here, you see the pixels are identified, then the features are converted. It identifies edges, then identifies the combination of edges, then identifies features like whether it is lip or nose or left eye or right eye or head or chin, whatever. And then finally it produces an output who the person is, or trying to identify the person, and it goes on. So we see how it does. Now skipping the regular, let's move on to the convolution part. So I'm not talking about the whole deep learning as such. I will only be talking about convolutional neural network. I hope you have a fair idea of what a neural network is, what we do in deep learning. Now let us move on to what convolution process is. If you have an idea of computer vision, you definitely have heard this name convolution. When we perform smoothing and edge detection or sharpening of images, we perform convolutions. We basically multiply a certain portion of the pixel values through a matrix which we call a kernel matrix. Convolutions are one of the most critical and fundamental building blocks in computer vision and image processing. So what do? We have a small matrix which we call as a convolution matrix or a kernel matrix. We convolve this matrix throughout the image. Okay, so we take this matrix, the small matrix, and we treat the whole image as a big matrix, and we take this small matrix in sliding window manner, and we keep multiplying it element by element. So convolution is nothing in deep learning terms, it's nothing but an element wise multiplication of two matrices followed by sum of all the products. So whatever multiplication we have performed, element by element multiplication, we add all these product results, and then I find out one sum, and that is the output of the convolution. So we take two matrices, both should have similar dimension, same dimension. In fact, when we take this small matrix, we put it over the big matrix to take a chunk out of it. We'll see. So we take two matrices which both have same dimension. We multiply these two matrices element by element. It is not a dot product, just a simple multiplication. And then sum the elements together. Although we say this is not a dot product, however, we are performing all the operations of dot product. Dot product also performs the same thing. When we have two vector, it performs the element by element multiplication and then summation of all the products which produces a dot product. So we perform the and this operation, the matrix being multiplied together and the all the products are added, is called convolution. Now there are two matrix analogy, big matrix and tiny matrix. Okay, we have a big matrix. So what do? I'll give you an example first with the big matrix, and then I'll come on to what do we do with the okay. So you see over here we have this example, and in this image, as you can see, there is a green matrix and there is a yellow matrix, right? Now if you observe the GIF which was running, okay, let me just show you. Now this is a GIF image. In this you see the bigger matrix is green matrix and the smaller matrix is yellow matrix. This yellow matrix is moving, first moving from left to right and then goes one row below, then moves from left to right, then again goes one row below and then moves from left to right, right? You see. And with every movement, it is producing some output on the right hand side matrix. So I have a bigger matrix that is 5 by 5, and then I have a smaller matrix that is 3 by 3. This smaller matrix is positioning itself on the bigger matrix and moving. With every movement, it is producing an output, and that output is being written over here. So if I could stop this and you see, if I try to calculate what is happening, you see I have this green matrix. So you understand this green matrix to be the matrix, the image. Okay, so I can have any image, and these values are the pixel values. Just imagine these values to be the pixel values. So 1 1 1, the bigger one that is written is the pixel value. This 0 is the pixel value, 0 is the pixel value of the image. Every image will have a pixel and pixel will have some value. So just imagine these are the pixel value. And then these small red numbers which are written over here are the values of the kernel matrix. So in a way, my kernel matrix has the value 100, 101, I'm sorry.
Muneendra sir, I think slide is not moving.
Which slide you are looking at, sir?
Now we are
Okay.
seeing slide number 27 or 28.
Okay, let me share the whole screen, then I think it will be visible.
Yes.
Also the slide, yeah, now slideshow is not on, sir.
One second. Are you able to see my screen?
Yes, screen is visible,
Yes,
sir.
My desktop is visible now?
Yes.
Yes, sir.
Okay, fine. Then it means that now my whole, now you see my slide?
Yes, sir.
Okay, then it means
But
now everything is shared. Yeah, 1 second.
it's not in slideshow mode, sir.
What about now?
Yeah, now, yes.
Yes,
Now,
yes, yes.
now
So
it's
you
fine.
see this GIF you are looking at?
Yes, 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 sir.
Okay, all right. Thank you. So I was fine. So, all right. So now you see this GIF and okay. Um, That's the problem, no? Okay, no issues. Just let me discuss it. So you see this GIF, and with every movement of this yellow matrix, as I told you, I think it was not visible. So we have the green matrix and we have a yellow matrix, right? The yellow matrix is the tiny matrix and the green matrix is the big matrix. So we have a big matrix and we have a tiny matrix. This big matrix, the green matrix, is the image. So you imagine it to be an image, and this image is what we are going to work upon. The tiny matrix, that is the yellow matrix, which is sliding from left to right, and then from left to right one row below, from left to right one row below, and like that it is moving. With every movement it is producing some numbers on the right hand side. You see the pink matrix. So with every movement it is producing some number. Now let me just full screen it, and at this point this GIF is not there, right? So you see what we observe over here is that there are some red numbers which are written and these black number. The bigger black number, that is 1, the big 1 is the pixel value of the image. Okay, this big 1 is the pixel value, 1 is the pixel value, and these small red numbers 1 0 1 0 1 0 and 1 0 1, these are the small red numbers which you imagine as the tiny matrix, or the kernel matrix. Where from these numbers are coming, you don't worry about that. We will come to that portion where we will have these numbers and we will learn how these numbers are created. But just imagine to understand the convolution process. What is the convolution process? So this convolution process says that we have a small matrix containing of numbers 1 0 1. I'm talking about the small numbers, right? So 1 0 1, then 0 1 0 and 1 0 1. Now if you multiply these big numbers with a small number, you see 1 versus 1 becomes 1, then 1 0 0, and this 1 into 1 is 1. So 1 over here, 1 over here, then again 0, then again 1. So third one, then a 0 multiplication, then 0 0, and then finally a fourth 1. Okay, so there are 9 multiplications, but out of 9 multiplication we get only 4 ones, and when we add these 4 ones together, the result is 4. Okay, so this 4, the pink 4, is an output of the convolution operation. What was the convolution operation? We take two matrices, multiply the matrices element by element, and then sum all the products, and that is what I have done over here. Element by element multiplication of black and red numbers. So 1 1 1 1 0 0 1 1 1 0 0 0 1 1 1 1 0 0 0 1 0 0 0 0 and 1 1 1. So there are 4 ones added together to give me an output of 4. If I run it, you see at every step a convolution is happening and the result of convolution is being written over here. But with this, you also observe that the size of the original matrix, that is the image, is reducing. The image was 5 by 5, now it has become 3 by 3. That is the result of this mathematical operation, the convolution. Because ultimately, after 9 multiplication, you are giving me one value. So how would the size remain same? Size would definitely decrease. Okay, size decreases. That is a common side effect. So we don't have to worry about this size decrease. Just observe the effects. So this is the convolution operation, and with this convolution operation we get the result, convolved features. Now I will take you back to the previous slides which I had skipped. Okay, and if I read it, you see an image is a matrix with a width, number of columns, with some height, that is number of rows, and some depth, number of channels. So all of us are doing this course on computer vision. So definitely you have a fair idea of what an image is. If I'm talking about an RGB image, then image will have a width, which is the number of columns, then height, which is the number of rows, and depth, the number of channel. If the image is RGB channel, it will have 3 channels. If it is grayscale, it will have 1 channel only. Okay, that depth changes. So we think of image as a big matrix, as I shown you in the green. So are you able to see this slide, big matrix, tiny matrix? Are you able to see this big matrix slide? Is my
Yes, sir.
slide
Yes.
changing,
Yes.
right? Fine. So we think of this big matrix as the image, the green that I saw, and the kernel, the yellow matrix, which was moving from left to right and top to bottom, as the kernel, the convolution matrix, the tiny matrix. This tiny matrix sits on top of the big image and slides from left to right first, then top to bottom, and then left to right, then top to bottom, and left to right. Applying convolution at each coordinate of the original image. So at each position, it applies a convolution. And as we saw in the example, the convolution produces a value which is what we store in the resulting matrix. So that is convolution. Now, why do we need convolution? What is the effect of this convolution? So there are few terms which I will coin here, which I will introduce here, and then I will explain the meaning of these terms. Like the first term or the first concept is a filter. Okay, what we are trying to do over here is we are trying to create a filter. Through this tiny matrix, we are trying to create a filter. What is a filter? Filter is something which filters something. Filter is a device with which you try to filter something out and obtain something in. Okay, like even if we try to filter milk, what we are doing? We have a strainer. Through the strainer, we filter the milk, and what is the result of that? There might be some something like some um, food particles, some hair of the cow or buffalo that comes in through the milkman. And when we filter, we get those impurities in the strainer, and what we get is the uh, filtered milk. Okay. So through filter, we try to stop something and we try to get something. So that is the objective of the filter. Okay. So we all understand what a filter is. What is a filter doing over here? A filter, we apply a filter on an image to obtain something and to discard something. Okay, the same concept, the same functionality is also applied over here. So what we are getting and what we are discarding, you see. Suppose I have to identify a pattern like this, the pattern that is given in front of you. This is a pattern, and this pattern says that there is a line which is starting from bottom, which goes in a vertical direction and then slightly bends towards a right hand side, my right hand side. Okay, so it bends towards right hand side. So this is a curve, it looks like a boomerang, and I want to find out all the curves which have this pattern. So my filter should be able to filter out this pattern and stop anything that is not this pattern. That is the objective of my filter. Why I'm doing it, I don't know. I'm a madman. I just want to see this pattern in my image. So I need to create a filter which will be able to find out this pattern, this boomerang pattern, and filter everything out. I don't want to see anything else. So what I'll do, I'll create an image like this, and what I'll do, I will put some values. If it is 0, as you can see over here, this is a matrix which says that, okay, in this matrix, everything is 0. If it is 0, it means it is hidden. And if it has a number greater than 0, like over here we have 30, it shows that, okay, there is some value, means it is an opening, and if it is 0, it means it is hidden. So I take this matrix and I put it over the image. So what happens? I'm trying to look through this slit. There is a slit and I'm trying to look through this. So basically this is a filter which tries to find out a certain feature. What are the features? This boomerang shape is a feature that I'm trying to find out. This boomerang shape in this case is useless, probably useless to us. But suppose this is the contour of an eye. Okay, so I create a filter which is just there to identify eyes. Wherever those eyes are in the image, I will take this filter, I'll put it over every portion of the image. Okay, and then I'll try to find out the feature of the eye or the pattern of the eye, like you see over here. So I have this pixel representation of filter on the right hand side. So this right hand side image is an image which looks like which is a filter for me. So I have all the pixel values zeroed out except this boomerang shape of 30, 30, 30, 30, 30. There are 7 values, 7 positions of pixel which have been made 30. Rest of the others are made 0. Now I take this filter, I am calling this a filter, this right hand side matrix. I take this filter and I superimpose it over this image on this portion, or this portion of the image, that's a cartoon mouse. So I have this cartoon mouse over here and I put this image filter over here. Now you see how we are visualizing it. So this is the receptive field. So the image is there, whole image, out of whole image, we take this small portion and we call it the receptive field, what we are receiving. So this is a visualization of the receptive field. The receptive field pixel representation looks like this. So all zeros and 30 over here. So this small 30 pixel over here, then 50, 50, 50, all 50, 50, 50, then some 50s over here, then 20 and 50s over here. So these pixel values represent some value over here. Now you see, with this, what I see over here is that rest of them are 0 and these values are have got some number. Now if we put this filter, the filter that I have created for finding out this boomerang pattern, and I superimpose it over here, or I say that I perform a convolution, then what will happen? You see, what is a convolution? Convolution is nothing but element by element multiplication and then summation of all of them. So what is happening? So for this pixel, you see, are you guys able to see the mouse pointer? My mouse pointer? Because I'm pointing through the mouse pointer. So if you are not able, it's very tough for me to tell you.
Yes,
I think it is visible.
Mouse
Yes.
pointer is visible. Okay,
Yes.
so I'm pointing because I was trying to get the pointer on the PPT, but it is now hidden with the taskbar of my screen, so I'm not able to get the mouse pointer from the PPT. Anyhow, this pointer should work. So you see this pixel, the rightmost uppermost pixel, 30 value in the receptive field, and my filter has got 0. So when 0 is multiplied with 30, it gives a result of 0. Similarly, this 30 multiplied with this 0 will give me 0. However, we move on. So these two zeros will result in 0. Now this 50 when multiplied with 30 will give me some value. So first multiplication over here, 50 versus 30. Then again this 50 give me 0, but this 20, 30, I think we are missing, yeah, 20, 30 over here. So 20, 30, and then 50, 30, then 50, 30, then 50, 30, this 50, 30, and then final 50, 30. I suppose this final 50, 30 is like this. So we have got all these pixels multiplied together and their sum will give me a value which is a very large number. Okay. Rest of them become 0. So I don't care for them. Whatever we are getting is a large number because of courtesy of some pixels which were looked through. Okay, so I got this filter and I got this filter which had this kind of arrangement. I can only see through this arrangement and I saw through this arrangement. What I saw was some pixels which were visible. So what I observe over here is that if it is a very big number, it means my filter was able to see a pattern similar to what I'm looking for. Okay. Now take another example over here. Suppose I take my filter, the same filter with which I'm trying to see a boomerang shape, and I place it over some other portion of the image. So my receptive field has changed. Receptive fields mean the field that I'm looking onto. So this receptive field has changed. Now this receptive field has got some different pixel arrangement. And now if I try to perform the convolution, what will happen? 30 into 0, 0. 30 into 0, 0, 30 into 0, 0, 30 into 0, 0, 30 into 0, 0, 30 into 0, 0. And none of the pixel values multiplication gave me any value which could be summed to obtain a big number. So if I'm getting a small number, it means the filter was not able to find the pattern that I'm looking for in the image on the portion that it is looking at. All right. So we observe few things over here, then I will move on. First, we observe that, okay, with filter, I was able to find out the pattern. Okay. So I have the same filter. I have the same filter that I took and I placed it over different portions of the image. So when I took this filter and placed it over here, this part of the image. So when my receptive field was this, I saw through the filter and I obtained the pattern. But when I change the receptive field and I put it over here, I did not obtain the pattern. I did not obtain a high value of convolution operation. Ultimately, whole machine learning, whole artificial intelligence, whole computer science boils down to some mathematical function. Okay, so every time we perform something, we perform any algorithm, that has to be converted to a mathematical function or mathematical model, or function is sufficient. So a mathematical function has to be there. Any operation should be able to, we should be able to explain any operation through some kind of mathematical function. And this is the mathematical function. So what we call as a filter is nothing but a convolution operation. However, the values are different. Okay. So I had this filter, I took it and scanned the whole image, right? I took it from left side and scanned the whole image. Then I went down and scanned the whole image. Then I went down and scanned the whole image from one filter only. And wherever I would get this kind of high value, not only 6600, the values might change, but wherever I will get this high number, a high number, I'll be able to say that, okay, if I'm getting a very high number, it means the pattern I'm looking for through the filter is present in that portion of the image. Okay, so can you not relate it to the recognition of eyes? Suppose I have a filter which is just created to identify eyes, contour of an eye. So where I will take that filter and I will scan the whole image. Wherever I have seen eyes, wherever the eyes will be present in the image, that filter will immediately raise alarm, give very high value that, okay, I have found eyes, I have found eyes. And if it has found eyes, definitely the eyes will definitely be on the face, and the chances, the probability of that portion of the image being a face will drastically increase, right? Now, so these are the filters. Now I relate from the conceptual terms to technical terms. So you understand what are filters. Now we have feature maps. You see, the image on which we apply the filter is called receptive field. Okay. So we took this, and this portion is called the receptive field. So this portion of the matrix is called a receptive field. This is a filter. The matrix which we are applying on to receptive field is the filter. So you see, this left matrix is receptive field and the right matrix is filter. So detect, what are we doing over here? We have this whole image, and on this whole image we have this filter. So you assume this to be filter, the small matrix with 4 cells to be filter, and the white portion is what is hidden, and the green portion is what we can see through. We take this filter and we apply over the image. So this portion, the first portion, the upper leftmost corner is the receptive field. We apply this filter on the receptive field and we try to find out whether the pattern is present or not. Okay. So the result of it comes over here like this. So we have 2 filters. We don't have only one filter. We have more than one filter. So when we have more than one filter, we apply all the filters onto the image on different receptive fields. So I'll take this upper filter and move it from left to right. Then I'll come one row below, then move it from left to right, then move it again from left to right, slide down, move it from left to right. And what I'm doing, I'm finding the features. What kind of feature? The pattern. What kind of pattern? The pattern which has two cells in vertical arrangement, and both of them are black. So you see, when I take this filter and I put it over here, I will not find two black pixels. But if I put this, so that is why this is white. But when I take this filter and put it over here, just the second row and the first column at the very beginning, but the second row. When I put it over here, I find two pixels which are black. And this filter was actually looking for a portion of the image which has two black pixels. And what it will do, it will immediately result in a black pixel over here, or it will identify. With that identification, we can do whatever we want, but it will identify this to be a pixel which pattern which has been identified. So as long as it identifies, it marks, and then it creates a convolution matrix. So this is the result of the convolution operation, and this result is what is a matrix. We call this a feature map. So when a filter is applied onto an image, the result is called feature map. Okay, so there are three terms we got now. One is the filter, the second is the receptive field, and the third one is the feature map. Fine. So in this image we had only two matrices. The left matrix is the receptive field, the right matrix is the filter, and the result of this convolution will be a third matrix. If we could create an equal to a third matrix, that matrix will be the feature map, the result of the convolution operation. The result is our feature map. So these are feature map. How many feature maps you will have? As many filters as you want to apply. जितने filter आप apply करना चाहेंगे, you will have those many feature map. With corresponding to every filter, we will have one feature map. So it is identifying the features on this map. It's like you are given an image and you are tasked with identifying all the trees over there in the image. So it is creating a map of all the trees. Okay, so wherever there is a tree on the image, you will just put a tick, or you will put a marker that, okay, there's a tree, there's a tree, there's a tree, or houses, where are the houses, where are the roads. So this feature map is a map which is depicting where all the features that I'm looking for through this filter were found in the image. Okay, so this is a feature map. So we understand what are filters and feature map. We understand what are kernels. Kernels are nothing but the convolution matrix, the tiny matrix. We get some values, and these values are convolved over the big image. Okay, so there are different ways of creating kernel matrix. We will see. We don't create kernel matrix. Kernel matrix is automatically created in the deep neural network. Okay, now we understood convolution operation. We understood three more terms: the filter, the receptive field, and the feature map. Now let us move on to our neural network understanding, and then I will try to merge two different understandings. So till now I was talking about computer vision, the image part, the image processing part, how we are actually dealing with image part. Then we also understood convolutions. Okay, what is the convolution operation? Everything was related to images only. Now let us understand the neural network part, because ultimately we have to map these two concepts. So understand the neural network, and then we will see what is happening. In the neural network concept, you see, I have a set of images, a set of pixels. First, try to visualize a neural network. What is a neural network? Neural network will have an input layer and then a hidden layer. Okay, when we have input layer in the traditional neural network case, all the input neurons are arranged in a linear fashion, in a vector, right? All the neurons will be arranged in a vector fashion. It will be a vector of neurons in a linear manner. However, there is a possibility that instead of linear vector, we can arrange the neurons in a matrix form, in two-dimensional format, in two-dimensional pattern, just like this. If we arrange it in a two-dimensional manner, in a two-dimensional pattern, we can project it as an image, we can imagine it as an image, and then we can work upon it. So let us arrange our input neuron in a matrix format, not in a vector format. So suppose these are input neurons. Okay, what you are seeing on left hand side are input neurons, and my input layer is arranged in a matrix format, not in a vector format. So this is a matrix format, and all the rings, the smaller rings, circles you are seeing over here are neurons. Now, in the traditional neural network, you would definitely have known this concept that all the neurons of input layer are connected to every neuron of hidden layer. So it is a fully connected neural network. But here I'm making another change. I'm not connecting all the neurons of input layer to all the neurons of hidden layer. I'm connecting only a portion of input neuron to certain neuron of the hidden layer. So what is happening over here? You see there are 5 by 5 circles or 5 by 5 neurons in the input layer, which are connected to first hidden layer neuron. Okay, so this is the first hidden layer, and this is the first neuron of the hidden layer. So instead of making it fully connected neural network, I am making it partially connected. And how I am connecting it? I am connecting first 5 by 5 block, first 5 by 5 block of neurons to the first neuron of the hidden layer. Okay, then I will shift this 5 by 5 block 1 pixel ahead or 1 neuron ahead, 1 column ahead, and then next 5 by 5 neurons. uh, uh, Dr. Verma, can I use some pointer in Microsoft Team, because I have not used Microsoft Team, so I'm not very aware. How can I utilize
Sir,
some
you can
point?
use a slide pointer.
Actually, slide pointer, it is hidden beneath my taskbar because I had to share the screen, right? So somehow it is hiding.
If you're right
Okay,
click on slide, and you will be able to select the pointer.
okay, let me just check.
First, yes, switch on in
Right
now. Right
click.
click and
Aha, very good, very good. Thank you so much. Thank you. I was okay, okay, okay. All right. Thank you so much. So you see now. So I have this 5 by 5 block that is connected to the first neuron of the hidden layer, right? Perfect. Now I take the second, okay, second block. So let me change the color, the ink color, and let me make it what, orange. Okay. So now this orange that I am looking, both colors are almost similar. Okay, same color. So this first block you saw, let me choose another block. So my next block starts from second column and goes up to this column, and this block. So first block of 5 by 5 neurons were connected to first neuron of the hidden layer. Next block of 5 by 5 neuron. So see, there are overlapping neurons. It's not like I will totally discard all these 5 neurons. I'm just discarding the first column of neuron. So these 4 by 5 columns, 4 by 5 neurons are still connected. But new column is now introduced. So I have 5 by 5 connected to first neuron. Now next 5 by 5 will be connected to second neuron, this neuron over here. All right. So this will be connected to this neuron. Now similarly, what I can do, you imagine over here. So I take very different portion of my screen. This set of 5 by 5, this set of 5 by 5. You can very easily guess that this set of 5 by 5 neuron will be connected to this neuron. Okay, this neuron. And similarly, the last set of 5 by 5 neurons will definitely be connected to the last neuron of the first hidden layer, just like this. So I'm taking one portion of the input neuron and connecting it to one neuron of hidden layer. Then another portion of input neurons and connecting it to another neuron of hidden layer. And it goes on like that. So all the neurons you see over here on the hidden layer are result of a connection from a portion of hidden layer, a portion of this, sorry, there are four, there should be five, okay, five. So five set of neurons, 5 by 5 neurons connected to some neuron of hidden layer. Now this way the convolution neural network is connected. Convolutional neural network is not fully connected. It is connected partially. And every neuron of hidden layer is connected to a locality of the input neuron. Okay, a locality of input neuron. How does it help? It helps in projecting the convolution operation onto neural network. Okay, so again reminding you, I first discussed the image, the convolution operation, and then I discussed the neural network connection, the structure of the neural network. Now I am going to merge these two. So what I'm going to do is take the convolution operation and put it over here on the neural network. Okay, so please pay attention. I think at this point of time is the crux of the convolutional neural network, because if you miss this point, you will not be able to relate to whatever we are going to discuss next. So this convolution neural network, this is a neural network which I call convolutional neural network, is not fully connected neural network. It is partially connected neural network, and every neuron of hidden layer is connected to a locality of the input neuron. Okay, or the next layer is connected to a locality of the previous layer. So there are a few things like it says over here: spatial extent, hyperparameter, receptive field, and so on. These I will discuss when. So now you understand the structure of the convolutional neural network. Now I'm going to take the convolution operation and apply it onto the neural network. How? You see, let me erase all the screen, all the ink on the slide, and then again draw something out for you. Right. You see, suppose you have a big image. So this is your input layer, input neuron. Okay. So you have this input layer of neurons, and this is your convolution matrix or tiny matrix or convolution or convolving matrix, which we call kernel. So what we do is that we take this kernel and we put it over a small portion of the input layer. Okay, we take this and put it over a small portion of input layer. What is this small portion of input layer? This same portion that is connected to the first neuron of the hidden layer. So just imagine the first neuron of the hidden layer. This neuron is connected to this region of the input layer. So I'm talking about this only. Now, so this region of the input layer, this region of the input layer, which I'm calling it receptive field, is connected to one neuron of the hidden layer. This is one neuron of the hidden layer. This is a hidden layer, total hidden layer, and this is the first neuron of the hidden layer. If my receptive field is connected to, if the receptive field is connected to first neuron, how is it connected? It is connected through edges. Of course, all the neurons of input layer are connected to hidden layer through edges, and you all know edges have got what? Every edge has got certain weight value. Okay, so if the edge has got a weight value, where are those weight values? So this kernel matrix comprises of those weight values. The W, X, Y, and Z that you see over here are the weight values. And the kernel matrix of the convolution operation acts as the weight matrix of the connection that I am drawing from input layer onto the hidden neuron. So this is input layer. This is one portion of input layer that I'm calling the receptive field. And this kernel is the weight matrix. I take this kernel and put it over here. Put it over here. And what will happen? So this is first neuron. Let me erase everything out and then redraw. So this is first neuron of the hidden layer, of the input layer, second neuron of the input layer, third neuron of the input layer, and fourth neuron of the input layer of this block 1, 2, 3, 4. 4 neurons are connected to this neuron of hidden layer, first neuron of the hidden layer. With every neuron there is an edge, and with every neuron there has to be a weight value. So W is the one corresponding to A, location of A. So W is weight value of this connection. X is corresponding to the position of B. So B will have X over here as the weight value. Y is corresponding to the position of E. So Y will be over here, weight value of this connection. And Z is corresponding to the position of F. So Z will be the weight value of this edge that is connecting this input neuron to this hidden neuron. So instead of this input and hidden connection being fully connected, it is partially connected. That is the property of convolutional neural network. And all these weight values are nothing but the kernel entry, kernel matrix entries, kernel matrix values corresponding to every neuron. So receptive field is 2 by 2. The kernel is 2 by 2. We have 4 values in the receptive field. We have 4 values in the kernel or the filter or the tiny matrix. Now what we do, we treat these kernel values as the weight value. So W corresponding to A, X corresponding to B, Y corresponding to E, and Z corresponding to F. Now what is happening when we take the weighted sum? Coming on to neural network. In neural network, what is the objective of a neuron? Neuron's objective is to perform a weighted sum, okay, and then pass that value to an activation function. So let us perform the weighted sum. How do we perform the weighted sum? We multiply the input value A with the weight value on its edge. So A into W, that is A into W. Then B into X, this is B into X. Then E into Y, E into Y, and then F into Z, this is F into Z, and we are performing weighted sum. So weight multiplication is done. Now we perform the sum. So AW plus BX plus EY plus FZ. Let me say that this is a value which is called R, the result of it. Okay, the result of this weighted sum. So don't you agree that this R is actually the result of the convolution operation that we have studied previously? What we did in convolution also, what I told you was multiplication of respective values, multiplication of A and W, multiplication of B and X, multiplication of E and Y, multiplication of F and Z, and then sum of all the products. This is what is happening over here. AW plus BX plus EY plus FZ. All these products are being added, and the result is what I got as R. So this R is nothing but the weighted sum of these input values, okay, and W, X, Y, Z are the weight values. So this is a weighted sum. Now R is what? R is result of the convolution being applied on this receptive field by the kernel, which is also acting as a weight matrix, okay, kernel which is also acting as a weight matrix. So if I go back and I look at this portion, you see, is it not having all the properties? It has a receptive field. Yes, this is a receptive field of 5 by 5 neurons, right? Now convolution operation, first matrix is receptive field. You see, in convolution operation, first matrix is the receptive field. This is the receptive field. Second matrix is the filter. This is the filter. And then third matrix is the feature map. This is supposed to be the feature map. Okay. Let's move on. Over here, I have the receptive field. This is the receptive field. Okay. Where is the second matrix? All these edges which are connecting the input layer neurons to the hidden layer neuron. All these edges will have weight values. They form the, so if I could change the color, let me change this color to blue. So these edge values, the weight values which are present on edges act as filters. So this is the first matrix is the receptive field, second matrix is the filter, and output of it is the result of convolution, which is the output given to the weighted sum given to the hidden neuron, the first neuron of the hidden layer. So this gets the weighted sum, and this is what is happening. So now this way we have taken the convolution operation and projected it onto neural network. A neural network which is not fully connected, it is partially connected, but that connection has a meaning. Okay. Now you see in this operation, if I just erase all the ink and then I tell you what is happening in this portion. In this portion, instead of putting the kernel at the very beginning, instead of putting the filter on the very beginning, I have slide it one step ahead. Okay, I slided it one step ahead. Now over here, what will happen? B will be multiplied with W, C will be multiplied with X, F will be multiplied with Y, and G will be multiplied with Z, and the result will be passed on to second neuron of the hidden layer. Second neuron of the hidden layer. This will create second neuron of the hidden layer. And understand one more thing. Since this kernel is moving in horizontal direction, how many steps will it take? First step, checking this receptive field. Second step, checking this receptive field. And third step, checking this receptive field. Okay. So in horizontal direction, how many receptive fields are there? 1, 2, and 3 receptive fields were there. So how many outputs will be generated? 3. So one output hidden neuron, second output hidden neuron, and third output hidden neuron. So the horizontal direction of the hidden layer will have 3 neurons in one row, and then this kernel need to come down. It will come down over here at the beginning, and that will correspond to this. That will correspond to this portion of the hidden layer. Okay, and similarly we will have this portion, we will have this portion, you see, and by having these 6 neurons, I will be able to cover 6 receptive fields of the input layer. Of the input layer, I will have 6 receptive fields. So corresponding to every receptive field, I will have 1 hidden neuron. So number of hidden neurons is decided by how many filters you will have, what is the input size, what is the step size, and so on. It is not something we decide that if we will have those many neurons in the hidden layer. In the convolutional neural network, it is decided with some mathematical function, how many neurons we will have. I hope I was able to give you a clear idea of what is a convolution operation, what is a convolutional neural network, and how convolution operation performs in the convolutional neural network. And this is the way this computation happens. This is the neural network arrangement. Okay, and let us move on to a few more concepts. Okay. Now, a convolution layer. What is a convolution layer? In neural network, in convolutional neural network, conv layer, which is in programming terminologies represented as conv layer, is the core building block of convolutional neural network. Conv layer parameter consists of set of k learnable filters. So all the filters, how many filters you want to apply, you will have to specify those filters, where each filter has a width and a height and are nearly always square. We take it to be square. Okay, sometimes some of the research papers tried with uneven cuboids, but those did not perform very well or did not give as good a result they were expecting. So there was no benefit having it. So it is always square because we need to specify only one value, and with that value you can tell what is the length and breadth of the cube. So we use a square normally. For input to CNN, the depth is the number of channel in the image and depth of RGB is 3, 1 for each channel. Now let's see. When we have a convolution layer, suppose this is the image, okay, and as you understand, every kernel acts as a filter. So how many filter you can have? You can have as many filters as you want. So you take one image and apply one kernel or one filter over it. So this filter will scroll from here to here, then here to here, then here to here, and after performing all the convolutions, it will create this feature map. Then you take another filter and perform the same operation on the same image, okay, and create another feature map. Then you take this filter and apply it over your image, perform the same operations of convolution, and you create third feature map. Take the fourth filter, perform the same operation of convolution and create the fourth feature map. So as many filters you will have, those many feature maps you will create. Okay, you can call it a feature map or an activation map. There are different names which have been coined. Why we call it activation map? Because after this we apply the activation function. Up to this point we have only obtained the weighted sum. We have not applied the activation function. So we apply activation function at this step. That is why some people also call it activation map. However, most of the time it is called a feature map because we obtain the features out of it. Okay. So at each convolution layer in a CNN, there are k kernels applied to input volume. Each of the k kernel is convolved with the input volume, and each kernel produces a two-dimensional output called an activation or feature map. Till this point, we have been looking at two-dimensional input layer. Now, what happens if we have a three-dimensional input layer? That is the case because our images may have more than one channel. If we have, you see in this case, RGB image, then there are three channels representing red, green and blue pixel values. So in that case, what happens? This is the image, the receptive field. Sorry, this is the receptive field. Okay, this is the receptive field. You understand there is a subtle difference between receptive field and the image. Images, this whole thing is image. But receptive field is that portion of the image on which we are going to apply the filter at this moment. So this is the receptive field. Receptive field is of the same size as the filter. So we have a filter, 3x3 filter, and depth of this filter is always equal to the depth of the image. So if the image has a depth of three channels, then filter will also be of the depth 3. So I have a 3x3 filter and 3x3x3 filter, which is being multiplied to this receptive field. And after multiplication, all the elements are multiplied. We get a single value, which is the result of the convolution operation. Now, it is important to emphasize again this asymmetry in how we treat the spatial dimension, width and height and depth dimension. The connections are local in space along width and height, but always full along the entire depth of the input volume. So depth will always be same as the input image. Depth of this filter will always be same as depth of the image. But this width and height may vary. Here I have taken 3x3. I can also take 5x5, 7x7, 9x9, 11x11, depending on you. Normally we take odd number. That is why I am saying I didn't say 2x2, 4x4, 6x6. Why we take odd? Because if it is odd, suppose 5x5, then I'll be able to find a center. Okay, central pixel, which we call, like over here, this is the central pixel of the kernel. Okay, and we say that this is the xy position at which we are multiplying. So normally we take odd dimensions. So height of this will be 3, width of this will be 3. Similarly, you can take height to be 5, width 5, height to be 7, width 7, and so on. Okay, but depth will always be same as the depth of the image. Now you see how this representation goes. You have an input image, which we call the input layer. It has 3 channels, red, green, blue, and we have certain number of filters. So how many filters do I have? 1, 2, 3, 4, 5, 6. 6 filters are here. Corresponding to every filter, when this filter is applied over this image, I get a feature map. And what is the feature map? This is the feature map, right? So this feature map is a result of application of this filter onto this image, right? Now what about this? This is the feature map obtained by this filter. This is the feature map obtained by this filter. This is the feature map obtained by this filter. This is the feature map obtained by this filter. And this is the feature map obtained by this filter in the volume 3-dimensional space, 3-dimensional space. So you see, I have an input layer, which is also 3-dimensional. Then I have certain set of filters. Filters are just the weight matrix. And the output of it is also 3-dimensional. The hidden layer is also not 2-dimensional, not 1-dimensional. It is 3-dimensional. And this whole thing is your hidden layer. This is hidden layer. And this whole thing is the input layer. This is input layer. And if we move on, you understand this is only hidden layer 1. From hidden layer 1, we can have hidden layer 2 also. Somewhere later, we will have hidden layer 2. So for hidden layer 2, this hidden layer 1 will act as input. So, and this thing will move on. It will go on. Things happen like this. Okay. And there are few terms which we all need to understand at this point of time. Spatial extent. Spatial extent is nothing but the step size you take. Okay. Oh, sorry, a receptive field size. Stride is the spatial extent is the size of the receptive field. Okay. Spatial extent is the size of the receptive field or size of the filter. Filters height and width. So spatial extent is being represented as E. It is the height and width of the filter. So what is the size of filter? Same will be the size of the receptive field. So either it is size of receptive field or filter side, doesn't matter. That is called spatial extent. Then we have depth. There are 2 types of depth, input depth and output depth. As you all understand, input depth is the depth of the input. Okay. So how many layers there are in the input layer, that decides the input depth. Similarly for H2, the hidden layer 2, the input is coming from hidden layer 1. Okay. So for H2, the input depth will be depth of this hidden layer. That is, in this case, is 6. This is 6. Right. For this I to H1, the input depth was 3. What is the output depth? Output depth depends upon how many filters we are applying over here. At any convolution layer, how many filters we are applying? We are applying 6 filters over here. That is why it has got a depth of 6. A depth of 6. So output depth is decided by how many filters we are applying, and input depth is decided by how many, what is the depth of the input that is coming to it. Okay. Next comes the stride. Stride is the step size. Step size means here you are taking this step size. So stride is 1, then we move the filter 1 pixel at a time. So from left to right, 1 pixel at a time. When stride is 2, we jump 2 pixels at a time. So not 1 pixel, we jump 2 pixels. Like over here, this is right. So this is the right. So this is the filter. This filter is being applied over here. So instead of applying on every this, we move. So we take it and we moved 1 pixel. So this 0, 1, 2, and then we skip 2 pixel. We move from 2 minus 1, 1. Then again we skip 2 pixel and 1 minus 3, 0 is what is connected. So we move 2 pixels. So how big a stride, how big a step, how big a jump we take, that is called stride. Then there is a concept of zero padding. As I told you previously, when we perform convolution operation, from input to output, the size decreases. Size decreases, like in this case. Here you see. So input size was 5 by 5. However, the output size is only 3 by 3. If you want to perform some kind of size matching, it will definitely not happen for all the images. But if you want to maintain, we perform some kind of padding. So padding is done in 3 different ways. There is a zero padding. So there are 3 different ways of padding. Zero padding, in which we just surround this image with certain values, and those values are 0. So all the way around this image we perform zero padding. 0, 0, zeros are given over here. Why we put 0, 0, 0? Because we want to start from the first pixel. So center of the filter, if this is the filter, center of the filter starts from the first pixel of the input layer. That is why we do some kind of padding. Padding can be any number of padding. You perform zero padding of 1 layer, you perform zero padding of 2 layer, 3 layer, that's up to you. Okay. So either you perform zero padding, so that my filter positions itself at the center of the filter, positions itself at the first neuron. So this is the objective of the padding. There are different ways of padding. What is other type of padding? See, as we saw, the first padding is called zero padding. There is some 2 different types of padding which you find in literature. One is neighborhood padding. In neighborhood padding, what we do is that instead of putting zeros, we put the neighboring value. So if it is 243, we write 243 over here. We write 243, 185 over here, 157 over here. We pad it with the neighboring values. Okay. Similarly, all these values will also be padded with the neighboring values. This is called neighborhood padding, because we say that with the pixel, 1 pixel change, the color contrast doesn't change too much. So we pad it with the neighboring values. There is another padding which is called circular padding. In circular padding, what we do, instead of writing it over here with the neighboring values, what we do is that we perform circular value writing. So we write 126. The end of the image will have whatever value will have be there at the end of the image, we write it at the beginning. So 225 will be written over here, and so on. Okay, and similarly this value 185 will be written over here, and we perform this circular pattern. And similarly horizontal, what happens in horizontal, same will happen in vertical. So over here I will have 218 and 84 will go over here like that. But these are all cumbersome processes and doesn't give very different result or very substantial output with the changing. So people stick to zero padding. There are benefits of zero padding, and several benefits of zero padding are there. So I think these are the concepts which so I explained spatial extent, we explained understood depth, we understood stride, we understood padding. That constitutes the whole neural network. Now, with these values, the spatial size of the output volume, as I told you, the hidden layer doesn't need to be specified how many neurons will there be in the hidden layer or the output layer. This comes out of the calculation of certain parameters. All these are hyperparameter. Why we call them hyperparameter? Because they are not computed automatically. You will have to specify their values. If we specify their values, this width W is the input volume, which is known from the image. F is the receptive field size. F is the receptive field size, means what is the filter size. Stride, how many steps you are taking, that is stride. And P is the amount of zero padding. How many steps of zero padding, how many columns, how many rows of zero padding you are doing. And this is the formula with which we compute what is the output volume. W minus F plus 2P upon S plus 1. So input volume minus filter size plus 2 padding upon S, the stride, plus 1 gives the output volume. However, you need to choose these values. If the input size is 10, means input size you don't have any control over it. Input size is input size, but you have control over P, F, and S. So F, P, and S should be so chosen.
Muneendra sir, you are not audible. I think some technical glitch at the end of a speaker. So wait a minute.
Am I audible now?
Yes, sir, you are audible.
What happened? Was I dropped only or
Yes,
something
yes,
else?
sir. You dropped
Okay,
only.
fine. Right. So these are the concepts that I have explained. We have these are the yeah. So I discussed about this output volume. I think we all listen to what input output volume is, right? So in a convolution layer, these are the parameters which we specify. Parameters are something which we have to tell to the system. Parameters are not which are calculated hyperparameters. They are not something which are calculated. Hyperparameters are those parameters which we have to specify. And we experiment with that. We experiment with different values. Like number of filters, how many filters you will have. This is something that cannot be learned. You will have to specify how many filters you want to implement in your system. Spatial extent E is tried B. Bias is also something you specify. Bias is something that it learns, but then padding is something which we have to specify. These are all hyperparameters. Okay, so I'll skip it and move on to yeah, there are different types of layers which we apply in the convolution layer. The first one is the convolution layer that I have already specified to you. Then we have an activation layer. As I told you in the convolution operation, we perform only weighted sum. We don't pass the weighted sum onto the activation layer, activation function. So this activation layer is actually one which acts as the activation, which implements the activation function. It takes the weighted sum, the convolution result of convolution operation, and passes it on to an activation function. Whatever activation function you want, you can call that activation function over here. Then we have a pooling layer, and after that we have fully connected and a dropout layer. So what is a pooling layer? In pooling, what we perform is we try to downsize the input. And for that, what we do is that, suppose take this example. Um, yes, take this example over here. We perform a downsampling, downsizing the input. So suppose our input is this size, 224 by 224 by 64, and I implement a pooling layer. So what pooling layer does is it downsamples the input, and how it does it? Suppose it takes a section of 2 by 2 pixels. Okay, 2 by 2 values. Out of 2 by 2 values, suppose it decides that it is going to do max pooling. Max pooling means whatever values there are, it will find out the maximum value. So it will take out the maximum value, and maximum out of these is 6. So 6 will be taken, and rest of them will be dropped. Similarly, out of these 2 by 2, it will take out the maximum, that is 8, and 8 will remain. it will be passed out of pooling layer and remaining will be dropped. So you see, out of 4 pixels, it dropped 2 pixels and took only 2 pixels. So the size is reducing. Size is reducing by half. It was initially 224 by 224. Now it has become 112 by 112. But the depth remains same, because depth is a result of an individual filter, because every depth slice is a feature map. We don't drop the feature map because every filter has found out some type of features. So we don't drop the features, we drop the input size. So input size was 224 by 224. We dropped it, down sampled it to 112 by 112. And this is how we perform the pooling. So out of there are 2 types of pooling: max pooling and average pooling. Ultimate result is one number. So if you perform a max pooling, take the maximum pixel value and pass it on to here. If you perform average pooling, then you will have to add all these pixel values, divide by 4, and then pass the number over here. Generally, people perform max pooling, and that is what I have shown over here. Right. Then you know the fully connected layer. Fully connected layer is nothing but the this two-dimensional layer, two-dimensional arrangement is converted, is flattened. Okay, we call this a flattening operation. Is this two-dimensional is converted into a single vector of values and then passed onto a fully connected layer. Fully connected layers are very similar to what you have understood in the fully connected neural network. All the neurons of input layer will be connected to all the neurons of the output layer or hidden layer. Now there is a concept of dropout. What are dropouts? Dropout is a kind of regularization technique which is implemented into neural network. We implement dropout between 2 fully connected layers. So how do we do it? When we have a fully connected layer, there and this is a very prevalent thing in neural network, that neural network tends to overfit. When it tends to overfit, what it does is that it the training accuracy versus the validation accuracy changes a lot. You will get a very good training accuracy totaling near 0, but the validation accuracy doesn't give you that kind of result, with the very good result. So that shows that model is overfitting onto the training examples. So to avoid overfitting, we implement dropouts. What do we do? How do we do dropouts? We switch off some of the neurons. Okay. So these neurons, some of the neurons are switched off, and this way we are promoting other neurons to perform the functionality of neurons that have been switched off. Okay, so what we do over here is that we promote. So these neurons have been switched off. So the other neuron, like this neuron or this neuron, is promoted, is pushed harder to perform the functionality that other neurons we are doing. Okay, so we kind of simulate an environment in which these neurons are not at all present. So 3 neurons are not present, they have been switched off. So what will happen if these neurons were not present? If these neurons were not present, then remaining neurons will have to perform the functionality of the neural network, what is expected by the neural network. So these neurons learn to generalize. Okay, and similarly, so at some point of time, some other neurons will be switched off. So this happens randomly. At some point of time, let's say the probability is 0.5, means 50% of neurons will be switched off. So out of 5, let's say 3 neurons or 2 neurons are being switched off. Over here you see 2 neurons were switched off. Over here 3 neurons. Randomly some neurons will be switched off at some point of time. So the remaining neuron will have to come up to the task, and they will have to learn the features that were being learned by these. The task that was being learned by these neurons will have to be learned by the neuron which are functioning. This way we promote the neurons to generalize, the neural network to generalize, and this way we try to avoid overfitting. So this is all. The layer pattern is something like this, in which we have one input layer. Then we have a conv-relu combination. Conv-relu combination means conv layer and then activation function layer. And this layer is repeated n times, where n is normally between 0 to 3. And then we apply a pool layer, or that also depends upon you. You want to apply pool layer or not. That is totally dependent on you, your choice. Then this combination is applied, repeated m times. M can be greater than 0 means you can have infinite number of this repetitions. Either you want to apply pooling or not, that's your choice, but then this combination can be repeated infinite number of times. Once you are done with this repetition, you apply a fully connected layer. Of course, that fully connected has to be appended with an activation layer. Here in this case it is ReLU, normally it is sigmoid or tan sigmoid. So fully to activation layer, and this is also repeated k times. K normally runs between 0 to 2, means you can have no fully connected or prefer to have two fully connected layer, and between two fully connected you apply a dropout, right? And at the end this FC is the output layer. And this way different case studies you will find that this is AlexNet, in which we started with 224 by 224 neurons, and the receptive field size in this case was 11 by 11, okay, and stride of 4, which gave and 95 filter, 95, 96, 96 filters were applied, right? So and the output was 55 by 55. So first hidden layer was of 55 by 55 height and width. The depth was 96 because 96 filters were applied. And then for first hidden layer, the receptive field size or the filter size was taken to be 5 by 5. And then how many filters? Then 256 filters were applied. The output volume came out to be 27 by 27. Then 3 by 3 filter was applied, and 384 filters were applied. This output volume came out to be 13 by 13 by 384. Then again 384 filters were applied, but the output, the receptive field was kept to be 3 by 3 only. This remains same. Then 256 filters were applied, receptive field size 3 by 3, and output volume came out to be 13 by 13. Then this 13 by 13 by 256 values were flattened so that they could be connected to first FC layer, fully connected layer, then second FC layer, then third FC layer, and then we had the output values. Okay. These are the different case studies you will find. Now, at this point, I would very quickly want to move on to the collab part, which will demonstrate to us how we perform classification. So I think we have almost 20 minutes, in which I will 25 minutes. I will quickly try to show you how we can utilize this to classify what is happening. See, what we discussed till now was all theoretical, and so are you able to see the collab screen?
Yes, sir.
Okay, great. So I will not run it. I will just demonstrate to you. Let me just zoom it a bit so that you have a fair idea of what is happening. All right. So this is a toy example in which we are trying to classify dog images versus cat images. You can find this. I'll share this collab file with your coordinator so that you all can access it. So we have this data set on Kaggle. We download it and we have some files. We import some libraries, and through these libraries we have to perform some action like OS, operating system library. We will be creating some directory shell utilities because we want to run some command onto our directory file. So what we do over here, first we download. Okay, so original dataset directory, we downloaded it over here. So this is the original dataset directory where you will store a smaller dataset. So for the sake of demonstration, I normally convert it to smaller dataset because the larger dataset takes days to train and then compute. So normally I make it a smaller dataset and put it over here. So this is the base directory. Then I create the base directory, okay, and call it base dir. So to run this mkdir commands, I need the OS library and shell utility so that I could run this onto my shell, onto my system. I could create this. So if you run this, you will be able to create the folders, copy the files from the original directory. This is the original dataset directory. From here to base directory, we will be creating all folders and we'll copy all files. So we need to create directories for training, validation and testing. We create it like this, then memkdirs for all of them, directory with training cat picture, directory with training dog picture, directory with validation cat picture, validation dog picture, directory with test cat picture and directory with test dog pictures. Here I have created 3 sections: testing, validation, training, validation and testing. Everyone should follow this kind of pattern. When you are doing machine learning, training and validation are very important. Without validation, you can never be sure whether your model is giving good result or it is overfitting. I will show you, my model was overfitting, and that can only be detected through validation. Most of the students skip this validation part, which is very important, and every time we catch them in Viva that why you have skipped the validation part. Anyway, so we have copied 1000 images into training, 500 to validation and 500 to testing. Similarly, 1000 images into training, 1000 dog images into training, 500 dog images into validation and 500 into testing. A total of 1000 cat images training, 1000 dog images training, 500 cat images validation, 500 dog images validation, testing 500 each. Now we have 2000 training images, 1000 validation images and 1000 test images. Here we are going to build our network. To build the network, we are applying Keras. We are not doing PyCharm. So in this, had we been doing PyTorch, we would have different code. I suppose many students and many participants would be doing PyTorch here. But I prefer Keras TensorFlow. So this code is in Keras only. From Keras, I import layers and models. Okay, so model is the general class with which we are going to create this object model sequential. We excuse me. So I'll be utilizing this sequential because my neural network will be sequential and all the layers will be in sequence. So I created an object of model class. This model will be having some layers. So we add layer. The first layer is the conv layer. Okay. Now we specify 32 filters and then receptive field size is 3 by 3. 3 by 3 means this value tells 3 as the 3 by 3 size, and this 3 says the stride. Okay. What is the stride? So 32 filters, 3 the receptive field size, 3 the stride, and then activation function is ReLU that I'm going to implement over here. In the first layer, as you all have seen the fully connected or the traditional neural network also, in the first layer we need to specify the input size. For remaining layers, the input size is automatically understood by the model. So we specify 150 by 150 by 3 means the image will be of 150 pixel by 150 pixel, and the 3 stands for RGB 3 channels. So first conv layer has 32 filters, and this 32 is what we are specifying. It is not a parameter that it will learn. It is a hyperparameter. Then second conv layer has 64 filters. Again, the same receptive field size and stride. Activation function is ReLU. I'm not specifying the input size because input shape or size because it is automatically understood. Then after so first conv layer, after that I am applying max pooling, and max pooling is 2 by 2 means 2 by 2 is the filter pool size and 2 is the stride. So 2 is the step size. So 2 by 2 is specified over here, and same goes with second layer conv layer, max pooling 2 by 2. Third conv layer has 128 filter and 3 stride, 3 receptive field size. Again the same ReLU activation function. Then I have max pooling 2 by 2. Then fourth conv layer has 128 filters, same 3 by 3 activation function ReLU and max pooling of 2 by 2. After these four conv layers, I apply a flattening operation. Flattening, what it will do, it will convert from 2-dimensional to 1 dimension such that it could be passed on to a dense layer. I need to put a dense layer over here, but I have taken it to be a flattened layer, which is a fully connected layer. After that, I apply a dropout of 0.5 in this case, right? So this 0.5 means a dropout of 50%. Then a dense layer of 512 neurons and activation function ReLU. You see the difference here. When we apply dense, when we call dense function, the number we specify as the first parameter is the number of neurons which we will have. However, in conv layer, we specify the number of filters. So conv 2D, we specify the number of filters, and dense, we specify the number of neurons that we will have. And final dense layer will have one neuron because we are doing a classification, binary classification. So binary classification can happen with one neuron only, neuron value 1 or 0 probability value, and that will give me the output of class 1 or class 0. In the output layer, we normally use sigmoid or softmax function. Sigmoid function gives a probability value between 0 to 1. That is why we use sigmoid, or softmax also can be used because it also gives us a probability value. Now you see, if we look at this model summary, you see this is the model that has been created. This shows layer and the type. Layer is con 2D number 8, con 2D, max pooling number 8, max pooling type. Okay. And this is also 2D, so that is why 2 written over here. Now the output shape, it says none 148 by 148 by 32. This output shape is automatically calculated. You see, 148 by 148 is calculated by looking at 150 by 150 was the input, right? From here, if you look at a 3 by 3 receptive field and 3 is tried, then definitely one from left side, one from right side, 2 pixels are gone. So it becomes 148, 148, right? And then output volume, output depth is 32. That is that it comes out from the number of filters that were taken in the con. So 32. Now what is none? None is the first parameter of this tensor because all of it is a tensor flow. So this output shape is expressed in terms of a tensor. The first parameter of every tensor is the number of samples. Now here we do not know number of sample, how many samples you will pass on to this tensor. So that is why it is specified as none. And same goes again with all the layers, you will get the same output volume depending upon what is your receptive field size, what is your stride size, and how many filters you have taken. That decides the output volume. Totally at the end you have 3,453,121 parameters that we learn. And in these, you remember one thing, at every layer, of course, the computing layer only, like conv layer, conv layer, conv layer, conv layer, this this flattened dense layer, and this dense layer, and this dense layer. Every layer where there is a computation happening, there will always be one bias attached to that layer. Okay, we don't miss the bias. So bias is always there, and that concludes that how many parameters we will have, including all the biases, we will have 3,453,121 parameters that needs to be learned when we train this neural network. Now, after that, we specify some more things like we specify the loss function with neural network. You understand it is a supervised learning mechanism. So we specify the loss function. We need to compare the expected output from the obtained output. And for that, we need to have a function. Normally, root mean square RMS values were used. Here we are using the binary cross entropy because it is a binary classification task. So we are using binary cross entropy. You have options of using whatever loss function you want to use for binary classifiers. There are different types of. So loss we are specifying as binary cross entropy loss function. Optimizer, just like the gradient descent or stochastic gradient descent you would have studied when you understand how a neural network learns. So there we perform the back propagation algorithm, right? So back propagation algorithm performs stochastic gradient descent, in which through gradient descent we optimize the values of the weights that are there on the edges. So what is the optimizer? There are different types of optimizer like gradient descent, stochastic gradient descent, batch gradient descent. Similarly, this RMS, ADAM, all of these are different types of optimizers. So here I'm using RMS prop. You can also use stochastic gradient descent, SGD. You can use ADAM. There are different versions which you can use. And the metric of we are going to use how good the model is performing. We are going to use the accuracy as the metric. After that, we perform some data processing. I'm not going to get into detail of that. With every example, you will have to perform some data processing. But the crux over here is this fit function. When we have created the neural network, we need to now train it. Training happens with the fit function. We call the fit function in Keras, and through that we perform the training. This is a special type of fit function which is called generator, fit generator. Here we utilize the generator function of Python, in which we are generating a batch of samples, batch of input sample. After performing these pre-processing, we perform these pre-processing, and like here this pre-processing is happening, and this fit generator calls the pre-processing function and then fits onto the neural network so that they could be trained. So here we are calling train generator. Train generator is the one which generates batches of samples. And how many steps per epoch? 100 steps per epoch. In one step we perform 100 batches. Okay, so 100 batches of samples are being trained in per epoch. How many epochs we will take? We will take 20 epoch, and the validation data is coming from validation generation and validation steps. There are 50 validation steps per epoch. Okay, so we call the fit function over here. This is the fitting process. You see validation accuracy starts from 0.5, then 0.5, 0.6, 0.6, 0.7, 0.8, 0.68, 0.7, 0.7, 0.6. Again, it remains in this range only of 0.7. However, the testing accuracy, this accuracy goes up to 0.86. Right. So validation accuracy is 0.7 and it has gone almost up to 0.86, means 879, something like that. Then after training the model, I have saved it. After saving, you see this is the curve, accuracy curve of validation and training. So dot represents the training accuracy. Training accuracy has gone up to 0.858687, while the validation accuracy settles down at 0.7475 something, right? Here also you see training and validation loss. You see this validation loss stops at 0.6 something. However, the training loss decreases down to 0.3532 something. So this is a classic example, classic curve of a model which is getting overfitted. Overfitting is happening over here, right? To remove overfitting, we perform data augmentation. I will not get into data augmentation. These are the techniques which you will learn through the different processes. Data augmentation, we do perform data augmentation because we want our models not to overfit, and through augmentation, we actually, what we do is that we augment the samples. We try to generalize. If our model is overfitting, it means it is learning the training samples too well. Okay, it is kind of cramming the same sample. So what we do, we change the input. How do we change input image? Like you see, this is the same cat image. Okay, 1, 2, 3, 4. There are 4 cat images, but we just translate it, rotate it, flip it. The cat size is face is right side, it is on left side. So flip it, twist it, rotate it, something like that. So if it has to identify a cat, all of these are cat images, but we force it not to learn it too well, not to overfit. We force it to generalize. Finally, what I wanted to demonstrate over here was that how does this classify? How does a convolution neural network classify? You see, it classifies through filters. There are different channels. When you look at all the filters,
I think again there is a technical glitch at the end of a speaker. So wait for a minute. All the participants are requested to be in a meeting. There is some technical glitch at end of the speaker. So wait for a minute. We are trying to resolve that. There is some technical issue at the end of our speaker, so he is not able to connect again. So we are going to end this session here. Sunil sir?
Yes, I think he was just about to end, but unfortunately got disconnected. Nevertheless, mostly he has covered his content. If there are some questions, then you can share on chat and we'll pass on. So with this, we thank Dr. Ojha for his insightful lecture and a lot of aspects he's discussed in CNN. Yeah.
Sir, my chat is not enabled and I have many queries regarding CNN. So, what to do?
Vijay sir, please enable the chat so that the candidates can ask questions.
Okay, sir, I will inform Vijay sir. I think he is not there.
Okay, sir. Because see, either you give the email ID of sir so that we can ping on that particular email ID for the query.
Lal Pratap sir, what you do, please share the email ID of Dr. Muneendra Ojha.
Yes, sir. Yes, sir. I will share the email ID of Muneendra sir in our WhatsApp group. Don't worry.
Okay, sir. Okay, thank you.
Okay, so that's all for this session. Second session will start at 12:45 p.m. So stay tuned. Thank you very much.